I'm going to give you, in my minutes, some perspectives of mine on performance tools, and hopefully those are complementary, I think, to the previous excellent talks, and tell you a little bit about TAL on the way. So here's the outline of how I'm going to approach this. I'll give you some motivation for about 5 minutes, I hope, not too much longer, then tell you more about TAL. I'll have to limit myself in how long I talk about TAL. And then give you some snapshots of experiences that we've had in applying TAL, just to give you a sense of how you would approach using this particular tool, and then wrap up with a little bit more perspective. So let me start here, because I think that it's important to kind of step back and ask ourselves, what is it that we are doing when we are using these tools? And I see this mainly as being a performance engineering process. It's a process by which we're applying these tools to understand what other performance complexities and inefficiencies within our program, and then use those tools to better understand how we are going to approach problem solving, the performance problem solving that we might have in particular. Now, what you've seen here in the last several talks is that there are a large number of tools, and I would say that all these tools are very, very strong and powerful tools, and I'm an advocate of integrated application of tools whenever you can use them together and merge them and take the advantages of the ones that you have available to you, because really this is a complex problem. We are tool developers. It's also a complex problem for us to try to deliver the capabilities to individuals to use. So what is this performance engineering process? If we think more of it as how to apply tools, what do we learn from the tools, what is the technology that we can use? From our point of view as a tool developer, we see this, I can see it, I'll just say this is what I think of when I think about the engineering process is a way of building some technology at different layers. I identify this as observation, experimentation, diagnosis, and tuning, by which we can deliver some of that capabilities for performance problem solving. That problem solving identified by these layers, which I think is relatively consistent across the different types of tools that you've heard about. So what would be observation technologies in support of looking at performance during execution by way of instrumentation, various types of measurement, using analysis tools to look at that performance data that you can capture. But that's not all there is. What we have in addition is technology that we could apply for doing experiment management, for helping to store the performance data. You're running experiments, doing performance testing, you're keeping around this information, and you want to support that experimentation methodology. But those experiments are going towards a certain type of problem solving. What is that that you are investigating? It could be scalability, it could be looking for bottlenecks within your code, it could be comparing different applications that do similar types of particular problem solving in science. And then tuning is the art of improving all of that for not only this generation of systems, but the next. So how do we improve this process? What is it that we can do as performance tools developers to give you better technology by which you can go off and do performance engineering, but also how are you involved in that process as well? We want to enhance this productivity of performance engineering. We want to do so in a way that is both leveraging the technology that we have, but is also engaging you as the users of the tools as part of that process. So in this particular case, I'm advocating the idea of having application-specific point of views in the performance tools, where the tools can provide you raw data, but if that can be coupled with also information that you provide as users of that tools, then it can enhance the ability of the tool to present performance information to you. We also have to be aware that we're not just looking at the application in isolation. We are looking at the application running on a particular system. The performance that you see is this optimized orchestration of a variety of things, the application code, the processors, the memory system, the networks, and the I/O. And if we only look at the application, we are getting this myopic view of performance. We need to have not only application-specific knowledge being brought to bear, but also considering what the system is doing in toto, not only the applications and libraries, but also the interactions or other users that might be on the system. So engineering encompasses a whole performance evaluation process as well. It's also important as we move forward and think about how to attack some of the issues in regards to increased complexity of these systems that we're going to need to start to introduce, especially within the tools, and you saw some of that today, some of the automated performance analysis and problem solving, identifying problems that exist within the executions, being able to do cross-experiment types of performance analysis, but also embedding within the tools themselves a knowledge discovery process that can take some of that information that you could provide to the tool, and there's needs to be ways to incorporate how to do that, along with what they understand about the system itself, about the processors and the architectures and so on. In a way, what this is really challenging us to do is to involve more of the users in this process. So we can talk about a performance engineering looking forward as being what I call here extreme performance engineering. It is bringing to bear all that we can in order to answer performance questions where we have the tools. If you've seen some of those presented today, and I'll talk more about the TAO tool, that being merged with other information that we might have that could come from other tools like performance modeling tools, but it also can come from a richer expression of what are the problems that are expected within the particular applications that we're trying to run on these large-scale systems, bringing all that information into, again, some other tool extensions that help in doing performance data mining, automated analysis, and expert reasoning about performance. So I think that was 5 minutes. We'll move to part two. Part two here, I'm going to tell you more about the TAO performance system, what we've been doing over the last 20 years. I think I have John beat on the number of years on this project, and then go and show some of the application. But what I want you to do as we go forward in the talk is think about yourself as being a part of this engineering process, thinking about how, in particular, this tool, HPC toolkit, some of the other ones that you've heard, could be applying to your particular performance problem-solving effort. So what is TAO? TAO, we initially conceived of it as being a framework for doing performance problem-solving that could hopefully continue for a while since the initial conception of it, targeting different parallel programming environments and paradigms, but it was also a toolkit, something that we would be continuing to develop and improve and trying to make better over time. Fundamentally, what it tries to do is support some mechanisms for performance measurement, profiling and tracing, and then the tools ecosystem around that supports that type of an approach, and see if we could apply it to the variety of systems that we have available. So in doing so, we started with a concept of what we might call a computation model that TAO was targeting would look like, and I think that this has been, for the most part, this diagram is probably 10 years old, and just in conceptualizing what it is that the system is presenting to us, both in terms of the hardware and how it's organized, the architecture of it, but also the perception of the software model, the parallel software model that's running on this system. And so we think intuitively about being able to try to capture information with regards to the physically distinct parts of the system, the nodes, as well as the context in which we are running processes and the threads, and that generally has carried forward well for us over time. TAO is fundamentally, at least it was traditionally, and continues to be primarily based upon a probe-based technique, in contrast to what John was talking about in terms of sampling and HPC toolkit implementation of that. TAO is trying to support probe-based measurement or direct measurement, where there are code that's inserted into the application, where events are being triggered by the code. The measurement system itself is picking up, seeing those event visibility, capturing performance information, and saving that as part of the execution. So the experimentation workflow that you would apply is to instrument your application. There are various things that we provide in support of that. Loading and linking of the TAO measurement library, you execute your code, you gather performance data, you make some options as a type of performance measurements that you want to make, profiles or tracing. You say something about the types of events and which ones you want to have activated, capture that information, and analyze the result. If you look from a point of view of what Tau system architecture looks like, then it's basically broken down into those three main components, providing some means for doing instrumentation. We'll talk a little bit more about that later on. That instrumentation is trying to provide a way to access the measurement API, which is linked in with your application. That measurement system itself, it has various ways to be configured so that you can capture the types of performance data that you would like. It produces profile or trace information, which we are then trying to analyze through some of the tools that we developed, but also tools that are leveraging other technology within the community. Okay. So the components, as you saw them on the previous slide, in a little bit more detail, are attempting to implement those capabilities through various features, I guess you would think about them, for the variety of problem and applications and systems that we would see out there. Our instrumentation can support a variety of languages, and they work with many of the programming environments that are available within the system today. The measurements system is trying to target both node level measurements as internode measurements, communications in particular, intranode measurements through threading of various sorts, plus heterogeneous systems where there is co-processor capabilities. That measurement is both gathering timing information as well as hardware counter information that's being made available primarily through the PAPI interface, and supporting both parallel profiling and tracing. There is an effort I'll talk just very briefly about for trying to integrate other tools that are having this common measurement platform into a core infrastructure, and that's called SCORE-P. I'll come back to that in just a bit. On the analysis front, then we're looking at how to provide tools for parallel profile analysis and visualization, but we're also looking at multi-experiment performance analysis through databases and tools that can do data mining over that data. Now, part of the problem here, as I think you heard it emphasized in the previous talks, is one of scale. It's one of the ever-increasing size and complexity of the systems. And so the tools that we develop, the technology that we try to implement, for these different parts are having to deal with their own fundamental challenges in terms of scale, getting access to data, being able to integrate with the other software infrastructure out there. And that's part of the tools, overall tools challenges. Just fairly quick, I'm going to move through this rather quickly. The instrumentation support that we have is for looking at a variety of different events within the code. That is both standard events, routines, classes, blocks, entries, loops, and so forth, as well as what you might define as events of interest yourself. These could be thought of as being abstract events. These are things that you could place at some point within your execution, but they also might carry some meaning that just in addition to where they might appear within your code. There's other things about instrumentation and about events that I don't have time to talk about. What we're trying to give you as the user is a way to express what you want to see in an application performance measurement. There's different mechanisms by which we can support instrumentation of your code from the source level all the way down to the binary instrumentation. And some of this is, sort of complex and sophisticated, but we're trying to automate as much of the process as possible. One of the things that we've developed is a way to wrap external libraries to try to automate the wrapping of libraries in different forms, where those libraries are provided to us in different forms, including ones where all we have is header files, and again, support the automation of doing so. This is tied in with the other technology we have for doing source level analysis and instrumentation, where we can, through some commercial grade parsers, allow for the analysis of your code to enable instrumentation of different parts, mostly those I listed on the previous slide in terms of events. But this technology could also be used to generate very easily and automatically wrappers of some of the libraries for instrumentation purposes. So moving forward into the measurement component, what we're trying to do within the measurement system is provide for portability and scalability of both profiling and tracing. Primarily, we are focusing on profiling because there's a good deal of other tools in the community that support parallel tracing in a quite sophisticated way. And what we would like to do is be able to leverage those tools and work with them as much as possible. There are some things that we can do in terms of tracing, in particular, that would allow for looking at different sorts of data, but the main capture of that information, keeping it in parallel trace files in a scalable way, is being handled in a more, I would say, sophisticated way by other tools, Scholastica and Scorpy in particular. With respect to parallel profiling, what we're attempting to do is to give a way of looking at different types of parallel profiles at different levels in which the events are appearing, as well as supporting the user-defined or more abstract events. And in particular, there is a technology that we've utilized that was a part of Samir Shindi's PhD thesis in mapping of performance events from one level of visibility to another, and I don't have time to go into that. It's being used, though, as an example, in part in what we call phase profiling, where if you have a different phase of your parallel execution, you can communicate that information to tau, and tau can then essentially bracket a performance measurement with respect to the different phases of your computation. Some of the tracking of I/O and memory is done through library wrapping, and then tracing is essentially implementation of all the events of interest that you would have with profiling, but in the form of capturing traces. Okay. Once we have profile and trace information, we've tried to build some tools primarily for looking at parallel profiles. This is the tool that we call Paraprof. And for capturing multi-experiment parallel profile data into a database we call TauDB, being able to then go and look at that multi-experiment information through a tool we call TauPerf Explorer. I'll talk a little bit about these in a few slides down the road here. For parallel trace analysis, I've been saying that we're trying to use other tools within the community. These are provided through Vampire and Vampire Server. You've heard about that earlier, as well as Scholastica. There's formats for traces that have been developed as part of a group of people looking at that problem. We're taking advantage of some of the other tools that are coming from that community as well. This is just a picture of the framework of what the profile analysis looks like. And I'll show you some examples of the use of Paraprof here as we go through the applications down the road. The performance data management, this is something that I felt was very important several years ago for trying to do two things. One is being able to manage performance data from experiments that you may have run with tools, but also perhaps trying to incorporate the parallel profile output from multiple tools into some representative reference format that could be stored by this database. And this is something that we have developed and now provide as part of the tau distribution. What we try to do within the database schema is really look at parallel performance profiles, but those profiles themselves can have various sorts of information associated with them, And so this just gives you a feel for what the schema of TauDB looks like. Now, one thing I want to emphasize that we try to do in the performance measurements that we support is to give you a way of capturing not only performance data, that is performance information, directly performance information, but also metadata, other information about your execution, about your anything that it might be. It could be coming from the way that you compiled your application. It could be coming from the system configuration at the time that you execute your program. It could be coming from things that you insert in the program that you want to tell Tau that this is metadata. This is important. It has to do with anything you can imagine, because we provide an API that gives you a key value pair type of mechanism for storing that along with your parallel profile. And I think that this is something that has been important to us and could be important to you as well. The tool that we have called Perf Explorer had the goal of being able to do some sort of systematic and scalable analysis across multiple experiments, implementing some sort of framework in which you could specify the types of analysis that you would like to do across those different experiments, utilizing some data mining technology through various statistics and data mining packages as a way of analyzing that data, and incorporating in particular the metadata for doing analysis, metadata analysis that might be of meaningful interest to you. And this just shows you the architecture of what Perf Explorer looks like, and we will see through some of the examples here in a second how this might be applied. But this is some work that came out of Kevin Huck's PhD thesis when he is now working with Tau, the Tau group. Both Paraprof and Perf Explorer are consumers, can consume performance information from TauDB. They hook up directly to the database, and this could be located, that database, both locally and remotely. I mentioned that we were trying to do some core integration. This is a project that we have had going on for the last 3 years with the Scholastica group. It's called SCORE-P, is the common infrastructure that tries to bring in the measurement capabilities, instrumentation and measurement capabilities across these different tools into a core measurement infrastructure. And I'm mentioning it here because there's not only was a mention of Scholastica earlier on, but also I think that this is an important thing for going forward. We are now targeting Tau to the core infrastructure that is being supported by SCORE-P. There's other things that we provide that SCORE-P doesn't as part of that infrastructure, but it's a real intention to have more integration and more leveraging within the community that does probe-based measurement, of which most of these tools actually do. So now what I'd like to do is shift to part 3, give you some sense of how Tau is being applied in some different application scenarios. You're going to have to tell me how much time I have left.
We have about 25.
Perfect. I'm not going to be able to show you all the applications that are in the slide deck, so I'm going to skip over. I think I've hidden those slides, but you have them in the slide deck that you can go and check out. Let's start with NWChem. Is one that is of interest, I think, to some of you. You probably maybe even have used it. We've had some interactions with Jeff Hammond over the last 3 years, and just looking at different things about NWChem, in particular things that are of interest to him to try to understand better of the performance. This is an interesting application because it's based upon global arrays, which provide one-sided access to arbitrary pieces of data, and so there's a challenge that we had initially is how do we work with such a library, one that's based upon this aggregate remote memory copy interface, ARMCI, as you'll see in the next slide, what we did. So that was an initial challenge, but there's other aspects of NWChem. It's an interesting enough framework that there's many different things to explore. One of those things had to do with just understanding better the scaling, one-sided communication for NWChem. It has different ways for it to be configured between a data server and compute process, where there could be a data server using a separate thread or not. And there was interest in trying to understand what that performance behavior would be like in those different options. And we also wanted to see how it scaled and what was particularly affecting the performance in that. So also understand trade-off of core allocations to the data server or to the compute part. So first we had to overcome the instrumentation challenge, and here what we did was to essentially develop an interposition library for ARMCI that allowed us to do the instrumentation that we needed to do for tau to capture all the calls that were coming into RMC. And so we did this following a technique that was commonly used in other purposes. We built the tau PARMC library. We wrapped certain other external libraries, and this allows for also some portability when we run across different platforms. The two at the time, the ones that were in the paper that you saw on the previous slide, were Fusion at Pacific Northwest National Labs, a Linux cluster, and Intrepid. So this is some output that came from some analysis from looking at the comparing and pinning and no pinning on some scaling runs where we tested it, in this case, for eight cores. This is in contrast to having a separate thread for a data server, which is not shown on this diagram. So what we're looking at is what happens when we don't have pinning. And this is in the left slide here, and what we see is that it just has very poor scaling. So as it increases in the number of processes, the communications overhead is growing in a very bad way. But if we use pinning, this is on the Fusion machine, the Linux cluster, then suddenly we get back that efficiency and we get scaling in the results. Now what this is showing you, just as an example, is the use of a Perfect Explorer for doing a multi-experiment analysis. Here we have a scaling study where we have 6 different executions across 2 different configurations, and the generation of the plots here is all automatic. This is the first time I think that you've seen this in this talk, what these parallel profiles look like, but the different colors represent the different events that we've measured, and so this is a scaling analysis, and what you can see just in the different color segments is how each one of those individual parts of the execution is scaling as you're increasing the number of processes. So I know it's a little bit hard to read from the back. If we move to a different machine, we have basically the same approach, the same setup. We're looking at the same type of scaling study. We're looking at the no pinning versus pinning scenario here as well, and we're testing it with both interrupt-driven as well as a communication helper thread. And what we see on this particular platform is that the ARMCI calls are barely noticeable because there is support within the architecture, for the communications. And we can have a whole variety of different other types of scenarios than we did in the paper for looking at NWChem and just trying to use the tools as a way to approach, in this case, performance problem solving exploration, performance exploration, if you want to think of it like that, where we're using the tools as a way to help us in that process. But we can do more. And in fact, recently there has been work done by David Ozog back here, along with Jeff Hammond again, looking at NWChem as it's applied to electronic structure, where we have the issue that parallel performance is determined not only by the systems on which you're running, the application code that you're running, but also by the problem, the nature and the characteristics of the problems that you're trying to solve. And in certain cases, like electronic structure and computational chemistry, you can have different problems exhibiting different behaviors, performance behaviors on the system. And this is what we have in this particular case. We have different examples here that will translate into different behaviors on the machine. How do we understand that? The issues that are associated with these different types of problems, seem to suggest that not only do we need to know something about, what is the sort of fundamental performance properties of the application that we are using, but also how they are being manifested in context of the problem that that application is trying to solve. Well, what is one of the more fundamental problems of NWChem is the reliance on an implementation where this next val variable is a global variable that is being updated to determine where to assign tasks. And this leads to scaling problems. You can see it here as we increase the number of cores, what's happening to the time per call of next val being a global value that is being updated. As the number of cores increases, that time per call is increasing. We can also see a little bit about how this compares to different problem scenarios where next val, as we're increasing the number of cores, is increasing in the amount of time that it takes for next val, but also has certain performance scaling problems at some point in terms of the percentage of the time that is taking up of the total computation. So what do we do about this? One of the things that David has been exploring is how to come up with a different algorithm to essentially eliminate the dependence upon next val in the computation. This different algorithm is based upon an inspector-executor approach where that has to, instead of having this global update, look for opportunities for understanding task assignments and then being able to load balance those out across the computation. So the question is, how well does that work? So we try to apply tau to try to investigate this. It's all summarized in this one slide where we have the original implementation with next val represented here in the color yellow. They tried to do some optimizations on the next val computation, and that had some performance effects as we see it here. This is from tau measurements of next val across, if this is not, you can't see in the back, across the process IDs for the entire execution. But now, if you apply an inspector-executor approach here, you can see for the first iteration the amount of time that's taken for initial inspection of where the tasks are and how the task sizes are distributed across the process ID. And then after that iteration, do some load balancing. And then the subsequent reduction in the execution time for the rest of the computation. So by switching from the original next val approach to the inspector-executor approach, there is a benefit of about 8%. Okay, so that's one type of application performance problem scenario. Here's another one. We're looking at a computation for climate modeling that is using multi-scale methods as a way to represent the problem using variable resolution meshing. Impasse is a software framework for doing rapid prototyping of these climate models, and in particular, the Impasse Ocean model. The Impasse O model is looking at ocean simulation, is trying to reproduce activity ocean phenomena, and it's using multi-scale meshing as a way to approach that problem. Now, if we use multi-scale methods, it's interesting to consider how the choice of meshing methodology within these applications is affecting performance. It's also important to look at how the implementation of the application on different hardware configurations is affecting performance. And Impasse O originally is a MPI application, and it has some performance scaling limitations because of that. And the developers are now trying to add OpenMP support. So how can we look at then the performance of MPAS, get the sense of the benefit of adding in the OpenMP element decomposition along with the MPI block decomposition to see what the performance benefits might be. Well, in doing so, as we'll see on the next slide, there was a improvement in the MPI performance by itself, but also if we look at other opportunities for performance improvement associated with OpenMP scheduling, then we'll get some additional benefits. So again, this goes back to being able, in the context of a problem-solving investigation, apply the tools, trying to understand how to capture performance that allows for the comparing, across different executions. Here's the original MPI scaling. It starts to fall off. We can see how this is associated with the different measurement events that we have done in this particular experiment, and see that mostly MPI events start to contribute to the reduction in scaling as we get out to larger sizes. We can then look at applying some of the different solvers in incorporating OpenMP, testing out the variety of cases where we have different number of cores and the allocations of those to the number of processes in various ways. And what we're seeing in these graphs also on the x-axis is the choice of the scheduling approach in the OpenMP parallel region to see what the benefits of making changes there are giving us. And what we can see a little bit better here in presentation of this performance information is that the default scheduling approach is generating a load imbalance where we had threads arriving at the boundary cell exchanges at different times. And what we can do is apply a different scheduling methodology in the OpenMP region to get a better balancing of that performance. Use of the tool, use of some of the visualization techniques here as a way to be able to contrast the different performance experiments and the benefits that they bring. Here is an execution of MPAS Ocean on Vesta up to 16K, and what we're just seeing here is some of the different events. We had the OpenMP worker threads as represented by this portion of the display, executing the solver routines, and the MPI weight master thread is what's doing the halo exchanges for this computation. Okay, moving along. You can give me a 5-minute warning, okay? It is 5 minutes?
5 to 6 minutes. Yeah.
Okay. I have 1 minute to talk about just XGC because it's an example of the use of the support that TAO has for doing GPU performance measurement. XGC is looking at problems in edge physics. I won't take too much time on the introduction of XGC, but what we're interested in doing is looking at its run on heterogeneous platforms, particularly when we're trying to understand how best to use a combination of the CPUs and the GPUs. We actually looked at XGC on 2 different systems, one that we have locally at the University of Oregon called Axis, which has a very similar architecture to Keeneland, and then also more recently Titan. It turns out that Axis is a little bit interesting because it has 3 GPUs per node, and those are sharing a PCI bus in sort of a non-uniform way. And you see a little bit more interesting performance behavior. But one of the things that we could do, and we could do this as well in Titan, is look at the trade-off of work assignment between the CPU and the GPU. You could run a variety of experiments making those trade-offs and seeing where you're getting the best performance between work sharing. So I will move on to looking at something else within the Axis machine where you're sharing the PCI bus in a non-uniform way, what this ends up leading to is a appearance within the communication associated with XGC that you have imbalances. And those imbalances are due really to the fact that you have slower memory copies happening on one side of the PCI bus just to get to two of the GPUs that are being shared by that PCI bus. And this leads to some imbalances that you see in the communication. And it's a little bit more evident when you look at that. But we also perform some of these GPU, CPU work sharing experiments on Titan just to show you that we are able to capture some of the performance data there and looking at ways to improve the GPU efficiency by increasing larger grid sizes. So I'm out of time, really? Okay, I have 4 more minutes. Okay, that's not bad. So, here's another application, and this will be my last one to talk about. This is work that Samir Shinde did here at Argonne with Jim Perez and Benjamin Chandran on IR MHD. And it is also can be found, this work that they did in the HP Source online magazine there. And what it's looking at is communication analysis for this particular application run on BGP and trying to identify opportunities for essentially communications performance improvements, but they found other opportunities as well for computation improvements. So the things that they identified here are ways to involve non-blocking communications, add more efficient implementation of an FFT library, and got a significant amount of performance improvement. I wanted to show you this because there's this other feature of Paraprof for doing a comparative analysis of experiments where you have the different profiles from different experiments shown here, and then you can see for the individual events that you've measured across all those experiments what the relative effects is in terms of improvements, and that's what we see here, from the original to the optimized communication to the improvement of the FFT library. They're investigating also some load imbalances. We could use some of the visualization techniques for looking at system topology, again, doing some of this comparative type of analysis to identify improvement effects. And then this is the last picture I shown here on Mira, looking at similar experiments where we're comparing oversubscribing of the nodes with additional MPI processes to see what the performance benefits of that are. Okay, so I'd like to just wrap up. In the beginning, I talked about some of the issues of performance engineering, but as we look forward, we're going to have some real challenges when we think about exascale machines. What we've talked about for the most part is what I would call first-person performance observability, that you're looking at performance from the perspective of the application. This is true for the most part for probe-based measurement systems. I think sampling-based systems and HPC toolkits in particular can also support looking at resources, which you might think of as third-person views, seeing how system activity is characterized at different levels, and the system resource usage is an issue. How are resources shared? The point of bringing this up is that as we look at exascale systems, it's going to be more the case that we need to have this coupled view of a first person and third person to understand what the relative contributions of using underlying resources are of the application, parts of the application that are executed on the machine. This may require us to do more online performance analysis, measurement and analysis using that performance information more online as a fundamentally different way of doing observation, where we're taking into account the effects of the execution in a dynamic way, utilizing those third person's view as a way of making online decisions about how resources should be allocated. I think this is going to be one of the harder challenges for tool developers going forward, and it's going to needing to have a significantly more integration in the Exascale software stack. There are projects in Exascale right now that are going on where we're looking specifically at this type of problem. You know, we have excellent tools. You're going to be using these tools today, you know, for looking at scalable parallel performance. But when we look forward, some of those tools are going to be needing to operate in a much more dynamic and resource-aware type of viewpoint. So that's it. I'm done.